No, I will try to make it today or tomorrow. And if not by weekend, please, like, send me like an email. You need to do that. Okay. Good. So I think we are ready now. Today we have colleagues of our joining us online from Egypt. They are very interesting to understand what we are doing. Sorry for our Egyptian colleague. Actually, we will like jump for you something because in the previous lecture we got some information. So I will review this information again, the structure of the lecture, and to see why today is important to have this data transformation and the principal component analysis. And I don't know if Soraya here or not. Not here, but actually this is very useful lecture for Soraya for her master work. But anyway, I will try to give like this an overview. So as you know, we will normally start with data collection, okay, and data collection. Data collection. And as we agreed, this data collection will be almost the last lecture, okay? And after the data collection, we start to go for data cleaning. After the data cleaning, we got some lectures about data statistics, like understand what's inside in data. And then we got data visualization, which is still, again, something related to this data statistic to understand what is going on. And Vicky helped us with part of the data visualization, which is QGIS. So actually, QGIS is part of the data visualization topic or lecture. And then last lecture, what we did, actually, we got the AIs, like introduction to machine learning and AI. Good. Today, we will go to something called principal component analysis. And this is data reduction method. Okay. And this is very simple. Why we are doing that? Say, for example, you are collecting data in your work, numerical data or social data. And this data actually is not only one variable. Actually, in your case, the case that you are choose, you have only two variables, right? The data that you are working on as a group, the master students. Only two, yeah. More than. Okay, how many? Okay, three. Okay, good. So what if we have more than three? We need to understand the relation between this variable before we start to make decision. Before we start to say this variable X is dependent on variable Y, for example, or there is a relation between that and that, or understand the problem. Okay, so we need to find the relation. How we can find the relation? We can find the relation by two ways. The first way, based on the statistic, we can look in detail in the statistic into the number, right? And we start to brainstorm, see the data in detail, and see how it's go, right? But this is actually I think the screen is shared, Dr. Ghunem. You see the data transformation. I think it's shared already. So you can see like the number through the statistic or visual. And the simple way of visualization is X and Y. Right? Try to draw a figure that show X and Y. Like if we have table, if we have table, for example, and this table include ten variable, X1, Y, Z, A, B, D, for example. Okay, so how we can understand the relation between these variables? Simply, we plot by plot X1 or X with Y. And then we see the points, right? Then we plot another one, X with Z. And then another one, X with A. And then X with B. And then Y with Z. Right? So we plot all the variables with each other in by plot in order to see the relation. If the correlation is positive, negative, there is no correlation, weak correlation, strong correlation, right? In order to understand this. So is this a simple way to go? What if we have 100 variables, for example? Right? What we can do if we have such 100 variables? This means you need to multiply. You need to multiply. You need to multiply this 100 by 99 by, it will be a very big number, right? So how we can do that? We need to do something called data transformation or dimension reduction. Okay, so principal component analysis is data transformation. We transform data to another type of data. So actually we will create new variables in order to reduce our components. Okay. So now we will go through the theoretical part, and then I will try to explain to you how we can do that. How we can do that? We will do it in three ways. We will do it by graphic, we will do it mathematics, and we will do it by Python. Okay, so just graphic and mathematics in order to understand the process behind it. We will not go to the mathematics deep, but we will focus mainly around the graphic things, how to do it in graphical way. The mathematic actually is the equation behind the graphic things. Okay, and then I will show you by the end of the lecture the Python code that should run this process just as our life. Okay. So this is just to link this lecture with the previous lecture. So actually, I now remember what the previous lecture was. Actually, it's about clustering. So in previous lecture, we got the different variables, different sample in our experiment, and we classify it into clusters. Okay, and we understand the different type of clusters, and we understood that T-mean cluster that we used in the previous lecture is unsupervised machine learning, and it's just one line. Put this line, and then you will have your clusters. Now we try to understand the characteristic features of these clusters. Okay, what's the relation between these clusters? How we can understand the different variable within each cluster. Okay, so in order to do so, we can have this very long bilateral figures in order to see the relation, or we can find it away with different way, which is the principal component. So what is the, before we go to the principal component analysis, we would like to introduce something called multi-factor analysis. Because actually multi-factor analysis and the principal component analysis is the same. Like principal component analysis is part of the multi-factor, and you can see from multi-factor, it's analysis that analyze data that include more than three components, three variables. So multi-factor analysis and the principal component analysis are both statistical technique, statistics. So it's mathematics used for data analysis, particularly in the field of multivariate analysis. However, there are some difference between the multi-factor analysis and the PCA, the principal component analysis. So in the multi-factor analysis is a general term that encompasses various statistical methods used to analyze data with multiple factors or variables. It includes techniques like factor analysis, cluster analysis, discriminant analysis. So actually, the cluster analysis that we did the previous lecture last week actually is part of this multi-factor analysis. This is important. The principal component analysis is a specific type of multi-factor analysis. So actually it's part of the multi-factor analysis. And it's used to transform the data set. Again, it's used to transform the data set to new coordinate system. By finding a set of orthogonal axes, it's called principal component, that captures the maximum variance in the data. It's primarily used for dimension reduction and identifies the most significant pattern in the data. Okay. So actually what we are doing, we are not just reducing the data. We try to find components that will give us a number. This number can describe our data. Okay. Now I try to explain it to you. Again, dimensional reduction. So in the multi-factor, some multi-factor analysis technique like factor analysis aim to reduce the dimension of the data. So dimension of the data, this means that if you have data that 100 variables, you just reduce them to 5. So instead of drawing figures for 100 variables, you just work with only 5. And this 5 include all the data within this 100, all the information within this 100. Principal component as is specifically designed for dimension reduction by transforming the original variable into a new set of uncorrelated variables, principal component, that represent most of the data viability. Okay. So now before we go further, because the rest is against theoretical background, so you can read it, but we need more about how we make it. So now we will use this example again. I hope our colleague online can see this. Not really, because... Well, now if we say we have a system that include only two variables, okay, X and Y. So our database just includes this 2 and 1. It's very simple. This is X, this is Y, this is our data when we are plotting it together. Okay. So the principal component analysis, something in order to increase the value of the data. And normally, if you have system, the principal component analysis is equal, the maximum number of principal component analysis is equal to the variable that you have. So if you have, for example, database that include 100 variable, you can get 100 principal components. Okay. If you have 1,000 variable, you can get 1,000 principal components. But only the first, second, and maybe third one include data, only the first 5, 6 variable include data that enough to define all the system. So in our case that we have only data include X and Y, how many components now we can get? 2. Okay. How we can plot these 2? Person can suggest our 2? Yeah, Y, in this case, Y is based on X, but if we would like to get this 2 principal component, flip this. Okay. We'll flip it just to make Mushtaq happy with this. This is Y, this is X. No change. Yeah, this is good point. Actually, we still need it. Why?
I'm happy.
But because we want to reduce the number of
Variables.
variables.
Yeah.
Minimum.
Yeah, but this is just to understand what this. So actually, I agree with Vicky and with you, Mushtaq. We can just go with X and Y. But this is just to see how the process is going. If you have like hundreds of the variables. Okay, but we still need to calculate the principal component as if you have just data that include 2 variables. Okay, why? Well, your database include X and Y, right? We will plot this data on X and we will plot it on Y. Or yeah, this X and Y. Make it like this. Okay, so when we plot this on X, this is the point where the data start, and this is the point where the data ends, right? And when we plot this data on Y, this is a point where the data starts, and this is a point where the data ends. Okay? Okay. The length along X and the length along Y, actually it's represent the information that we can get from the data. Okay? So if you look here, this is the length along X. Make it here just to make you visual for you. Okay, and this is the length along Y. X, this is Y. Okay. Can we measure the length that has this orthogonal dimension on the X and Y and see if the length is more or less? Like this one. Start from here up to here. And if we make it here like this, larger, right? So actually it's include more information than just exam. Okay, so it's include more information than exam because it's more length. And this one is the BC1. So this is actually the BC1, the principal component number one. Question online? Yes. Yes, Raya? Unmute yourself and ask Soraya.
Hi, doctor. We can see on the board.
Yes, because it's a bit far away. Yeah, but just for 1 second, and then we will go back to the presentation.
Okay, thanks, doctor.
Yep. Okay, so actually this is the principal component one. Do you know where is the principal component two in this system? No, because we said that principal component is equal to the number of the variables. So if we have two variables, this means that we have two principal components. Any suggestion? I will try to just zoom in for the people online. Any suggestion?
Hello, can you hear me? Kata speaking.
Yes. Yeah, Kata. You are not here today, Kata.
I am not. I'm sorry. I'm afraid that
Oh.
from now on I can't attend the lectures personally that are in the morning, but
Okay,
I
please
will
ask.
try the best I can to attend online. So just if I understand the question correctly, we have a certain number of variables, and if we have two variables, then we have the minimal number of principal components equals to 2.
The maximum number of principal components equal to 2.
Oh, but that's also the minimum, isn't it? To define an equation, we need two variables at least, no?
Actually, the minimum, it's depend on the researcher who can decide on the minimum. For this example, you can say I have only one principal.
Oh.
But the maximum is equal to the number of the variable. In this case, the maximum is 2.
Okay.
Yeah.
And now we are searching for the other one.
Now we are searching for the other one. Yes. Based on the graphic. So now
it's still quite hard to see it. So I think this is my input. Sorry.
Try to. I hope now it's clear somehow. So
okay.
Yeah, this is the X variables, This is the y, and this is the points. And then we found that the principal component is the line that has a long, or that can connect the data along their long axis. Okay. Okay, this is the principal component 1. So my question is where we can find principal component 2? Any suggestion from here, people at class or online, or suggestion?
Does it have to be on the line that you drew?
No, it should be between the data.
Going in this direction.
Mhm.
So maybe explaining kind of this direction. Does it make sense? Like, I don't even know how to explain it.
Yeah, makes sense. Like the right angle to this one. So if this is the one that is the principal component, so the second component most probably will be BC2. And then if you plot this data, it will be, it include information from here up to somewhere here. So this is the BC1, this is the BC2. You didn't have with this. Yes, it doesn't have enough information. This is correct. But principal component 1 has. Principal component 2 has less information. And if we have a more complicated system and we go to principal component 3, we'll have more less information than principal component 2. And the principal component 4 will have more less information than principal component 3, and so on. So actually, principal component 1 includes the most information about the system. And then 2, less information. 3, less information. 4, less information, and so on. And this is why we said in a system that include 100 variable, you can create 100 principal components, right? But you can use only 3. Because all the information in the system can be defined only by the first 3. First component, second component, and third component, and that's enough. Or 4. This is the idea. So the idea is to try to create new variables. This is new variables. This is BC1, BC2 is completely new variables. It's independent on each other, but it includes the data. It includes the information from all the other variables. And there is equation for that. When we'll come to the mathematical part of the lecture, there is equation that defines the relation between principal component 1 and the other variable, principal component 2 and the rest of the variables. Okay. I still see some question mark. You have something? Question marks?
Might get the answer for this when we are working more with it. But I'm just trying to make it sense in my head. So if we then, for example, have the example we have here with the X, Y, Z, A, B, D, will you then make these examples you made here? Then you get the principal component of each of these. You end up, and then say if we only use PC1 and PC2, then we will just have 2 variables for
To define the system.
Okay.
Yes.
So that's the
Yes.
all we have to, actually. If we just choose this
Yeah, or 3.
or 3.
Or 3.
Okay.
So actually, this is exactly what you said now. When we try to plot, actually, it's not only 2x and y, it can be complicated in 3 dimension. So now I can explain you the 3 dimension one just to understand a bit more deep, but this is how it should work. So how it should work, you start to make variable 1, variable 2, x and y. and get the principal component. And then variable 2 and variable 3 and get the principal component, and so on and so on. Okay. In mathematic way, we will create like a correlation coefficient matrix. And this correlation coefficient matrix between the different variable is the equation that define principal component 1 and principal component. Of course, when we go to the real world, you don't need to do so. You need just to understand one line that already trained by some data where it's able, the Python code, to understand your data and get your principal component 1 and the principal. Yeah. Okay, so now if we assume that our database includes 3 variables, X, Y, and Z. Okay, what we should do? How many variables how many principal components we have? Okay, 3, and we have 3 dimension. So this figure actually will be a bit more complicated. I will try to make it here. So I need now to zoom out. Okay, so I will try to make it here. Like this is X, this is Y, the same figure, and this is Z. 3 dimension. Okay, and our data is plotted here. You can imagine it? Good. The long axis of the data, we can just try to centralize a line between the data, and this is principal component 1. Okay, now we define the principal component 1 visually. The plane that is perpendicular to this line include principal component 2 and the principal component 3. Okay, so if we assume that this is a line here, I will leave this. This is a line here, and we have a plane that is perpendicular to this line like this. Principal component 2 and the principal component 3 actually within this plane. And then we can just get this plane, which will be in this case 2 dimension, because this is a plane, this is only 2 dimension. We get it, the data is here. We can calculate the first component for this system, which will be the second component, and the second component, which will be for the full system, the third component. Make sense? And if we have four variable, the system will be a bit more complicated, but still can be visualized, like it will be in 4D. If we have 6 variable, 7 variable, again we can make it, but it will be much more complicated. Okay? Okay, good. Any question from online people? Kata, do you have any question? No. Soraya, you have any question? Yeah, please, Kata, you have something?
As far as I understand, the principal components are spatial definitions of our data set.
Not a special definition, it's a way in order to reduce the dimension of your data set. In order to be able to present your data set in a better way. So if you have a data that include 100 variable, it will be so difficult to understand the relation between these 100 variables, right? But it will be much easy if you start to analyze this 100 variable into, for example, 4 principal components, and then you can start understand the relation between these 4 components. Did you get it? Kata, you still with me? Yeah, I think she did it, but yeah. Any other question from online people? Okay. So we can still read the theoretical part. And again, why the theoretical part is important? Because the exam will come from the theoretical part. So multi-factor analysis, we still going around this multi-factor and principal component. Multi-factor analysis, the interpretation of results in multi-factor analysis depend on the specific technique used. So for example, factor analysis may provide insight into underlying factors deriving by observed correlation between variables. Cluster analysis, for example, is multi-factor analysis, right? And when we did it, it will give us like clusters. So actually the different analysis in the multi-factor give you different type of data. And if you understand now what we are doing, now we are going to the data interpretation. We try to interpret the data. We try to see how these factors are interact with each other. Okay. Good. In principal component are orthogonal and sorted based on the amount of variance they explain in the original data. The first component analysis explains the most variance. Again, the first principal component explains the most variance, and subsequent component explain decreasing amount of variance. And this is what Mushtaq already observed when he say second principal component is not the same length as the first one. It's correct because the main data goes to the first one, and then less data or less information go to the second one, and less will go to the third one also. Yeah. Good. Here's some assumption for the multi-factor analysis. The different multi-factor analysis technique have their own assumption because you have it's different methods and you have different assumptions. Okay, so for example, the cluster analysis that we did last week, we assume that our sample has a relation and it can be clustered within some groups, and based on that we start to work. But if we know from start point this data has no relation, like a point of data that collected around the student in Tromsø, another point of data about the car in Norway, third point about the market in America. What's the relation between these points? It's different data. We can't make a cluster out of it, but we assume for the cluster analysis that the data are almost the same, so we can define some groups within the data. For the first principal component analysis, we assume that the variables are linearly related, so there is linear correlation between them and normally distributed. So the data is distributed along this line is almost equally distributed. Okay, this is the two assumptions behind this process. Okay. This is just again some theoretical background, which is why we need this multi-variable analysis. I don't know why this point alone, because you know it's our data is huge normally, especially when you are going to work with big data, not only with 3 variables as you did, but if you are working with 100, 200, or 1,000, for example, you need to understand what's the relation between them, right? And again, if you would start to plot X and Y, you can understand the relation, no problem, but it will take years. And this is a quickly way to extract useful information. There's just some blah, blah, blah. This is why we have a lot of data, like, you know, we produce data from mobile, from from mobile, from computer, from chemical labs, from biological lab, from citizen science. We have a lot of tools of data that collect a huge amount of data, and all of this data are linked together, and we need to understand the relation. Again, this is a problem. It's not easy to visualize this data. The best way is the bivariant plot. So the best way to visualize this data is the bivariant plot, which is something like this. So this is actually variable 1, variable 2, variable 3, variable 100 variable, and 100 variable. And within each one, you draw like X and Y, and you start to look at the correlation. You can do that, no problem. Okay, but it will take some time, months, 2 months, 3 months. Maybe when you finish your PhD or master, you will finish this, right? But you're able to do it. So for example, for our colleagues online, for example, you, Soraya, you can actually plot the chemical analysis that you have, X and Y, against each other. And you will get such figure. And then good luck with the analysis that you will do if you succeed to do it. Right? It's not easy. So how we can visualize the problem? We can visualize it in 2D, we can visualize it in 3D, as we just make the example now with the 3 bins, or we can visualize it in 4, 5, 6D. Everything is possible. So we can visualize it in 6D, no problem. Okay, but how to extract the data out of it? This is the point. Okay. So this is an example of X and Y visualization. Again, we don't need to go here because it's simple things. This is just to understand that when we start to make principal component 1, principal component 2, principal component 3, I don't know why this thing is going on. Principal component 3 and so on, we have information which will be captured in principal component 1, 2, and 3, and so on. But when we calculate the factor, the load of this principal component, the weight of them, it will not be 100%. It will be 100% only if we got all the principal components, which will not be useful, of course, because you know what's the point to have a database that include 100 variable and create 100 principal components. Actually, now you are just go to a complicated things because now you have a database with 200 variables and you need to analyze this, right? But if you look at the first 3, 4, 5 principal component, and this for each component there is a weight, as we will see in a few minutes. If you start to collect this weight for first, second, third, and fourth, your total sum for this weight will be 99%, 98%. Okay, this 99% is the information in the data. And the rest, the 2% or the 1% or 1.5%, this is a noise in the data. Sorry? You didn't get this? Okay, so now we agreed we will not create 100 principal components. Okay, how many components we will create? Say 5. Based on what? Yeah. Yes, exactly. So exactly, Mushtaq, make it like visually. So you will get the length of principal component 1 and collect it to the length of the principal component 2 and collect it to the length of the third principal component. And this collection will give you a sum. The first one will be in total, if you make it like 100%, will be, say, 50%, 60%. So it's captured only 60% of the data. So we need more data. So we will get the second component, and this is 20%. So 20 plus 70, we are 80, right? And then we get the third component, which will be much more smaller in the size. And this is maybe 5%. So now we're 85. Are you happy with 85? I am happy with 85. Okay. I will start to analyze my data with only 3 components. No, I am not happy. I need to add the fourth component. Okay. Go for the fourth component, which will be just 3 centimeter. Okay. And this 3 centimeter plus the 95 will be almost 98, 99. Okay. It's 99. So now I have 4 components that include 99 of the information of the data. I am happy now. Okay, I will go to start to analysis. So actually, this information, this 99 is information, and the rest is just noise. Got it? Got it, Fikri? Yes. Well, it's depend on if you are working on numerical data, you can get something close, very close to 100. Not, of course, you will not reach 100, because if you need to reach 100, you need to get this principal component equal to your variable. If you are working with social data, it's a bit complicated. You was working with social or no? Yeah. Yeah. Because again, it's based on the system. Like for example, if you are in a lab and you know your system and you collect the observation in the lab, which is closed system somehow, you understand, okay, this variable is depend on that variable. So when you start to make this principal component, you will collect the 100 or almost 100. Okay. But if you are in the field and you collect field observation, it's different. Right? Because most probably there is some variable that you didn't collect and it's affect the system. And this is why you get just 50%, because there is other 50% that you didn't collect or you didn't observe, or for some reason there is problem with this because it's open lab. It's a natural. Yes. Yes. So it's depend on the type of the analysis that you are doing. Okay, for your case, 50%, we have here a real case, 50% is fine, no problem. And she start to analyze her data, she happy. In other case, no, I need to have 90%, 95%. So it's depend on what you would like to get out of the data. So basics of the principal component. Principal component is useful when we need to extract useful information from multivariate data sets. This technique is based on reduced dimension. So actually we reduce the dimension from 100 variable, from 100 to only 3 or 4. So this is reduced dimension. And the aim is to make it easy to visualize the data and understand the data and start to analyze the data. Okay. Maybe we can have like a break for 10 minutes. Okay, so we can come back or meet back in 11:15. Okay, our colleague online, we can come back in 10 minutes.
Okay, I'm waiting for the next lecture. But
Yep.
anyway, I have a question. It is
Please.
The principal components do you make? Did it in one and the same type of variety? So I mean, for example, figure varieties, numbers, field data varieties, and what I have to collect between these different varieties. The principal component should be one and the same type of
No,
variable? This is
no,
the question.
not necessarily, because we can make a relation between field observation, for example, and geochemical data. So it's two different type of data. We have this field observation, which is field variables, and we have the geochemical data. So it's completely two different type of data, but we still can make this correlation, and we still can get the B principal component out of it.
So how we can eliminate our data to make a principal component for different types of variables?
Well, I think this is a very good question. It will come in the coming slides. We need to scale down or scale up our data. And this is something very, very important. So if you are using, for example, field data, field observation, you can't start from first step to correlate it with geochemical data. Okay, we need to scale both data in order to use them, and there is a reason behind that. That actually the principal component measure the weight of each variable in your data. So if we assume that, I will give an example from geology. If you are working with granitic rocks, and the granitic rocks, the silica is more than 80%, 70%. And all the analysis, all the silica is around 70, 80, 75, 65, something like this. And the rest of the elements is 2, 3, 4, 5%. Okay, the principal component will give the high weight for the silica. And this is wrong. Because maybe the factor that captions the difference in the system is potassium, for example, which is just 1%. So what we need to do is to scale up and down the different variable in order to make this principal component. But this is one of the slides that we will explain in few minutes.
Thank you so much.
Thanks. Well, for our colleagues here and Kata and Victor, I sent yesterday an email. You receive it? Good.
Yes,
There is a total survey. I hope you can just fill all the time slots that available for you. Okay, based on this voting, we will make one extra lecture or two extra lecture, depend on. If we make one extra lecture, just to motivate you, if we make one extra lecture, we will end early December. Okay, and we will end. If we make two extra lecture, we will end early December, but with social event, so we can bring some pizza and we can eat together. So it's up to you. And I hope you to make it very fast, like maybe today or tomorrow, just to fix this problem, because if we didn't make it this week, we don't know what's the timetable next week. Already. Okay. So I hope all of you, just to make everyone happy, you reply. Okay.
my group meeting.
Yep. Make it in the group meeting of Ustad.
Visualize data in XV.
Yes.
How would you do that? I've never seen visualization of data in XV.
I can show you something, but don't. Yeah, here. Don't be. What's this? Okay. or figures, just to make it easy. I think it's easy to visualize data in 4D, right? 4D makes sense. Yeah. In this case, you need to, like, I will give you an example of this one. Of course, there is different way to visualize the data in more than 2D or 3D, but I will give you an example. Not here, unfortunately. Maybe this one, maybe. And go for this. No, maybe this one better. No, fine. New modeling, maybe. We are looking for yes. This is an example. So actually, this is visualization of data, thermodynamic data. And it's actually, I didn't remember the system, but I think this data is presented in 9D. 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 Well, it's a bit difficult to interpret this. So you need to be trained very well to understand this. But this is 9D figure. So actually, this figure is projection. It's projection. So actually, you are working with 2D. So you see the data in 2D. But if you can imagine it, this is actually in 9 dimension. So it's 9 dimension. And in each dimension, you have elements. For example, silica, magnesium, alumina, okay? And your sample or your projection is lay between this dimension and you plot it in 2D. So it's not easy to visualize it, not easy to calculate it. So actually this figure, like, maybe you spend 2 months just to calculate it, but it's actually 3 or 9D figure. Well, actually you are plotting it here from only 2 axes because, yeah. Well, it's a bit tricky to imagine it unless you start to go point by point. So you can go, for example, I would like to see what is here. Okay. And then here you can say, okay, here I have my silica component is like this. My sodium is like this. My alumina is like this, the 9 dimension, and the pressure and the temperature. So actually this is more than, this is pressure, temperature, assemblage, and 9. So it's 12 component. It's 12 component figure. Yeah, you can't see it. You can't see it. But you can. So in general, you can present your data in more than 4D. But again, it would be so difficult. So it's not easy to read, not easy to interpret, not easy to understand. Not everyone can understand this, for example. Okay. So, and the point of the science is to simplify things for the reader. And this is why we try to go for this principle. Yeah, it seemed to be, yeah. Yeah, you can imagine it's 2D, but actually it's not 2D, it's 12. It's 12D. And you can really, can take 6 months just to calculate this one. Just to fix the plane that you project from it. No, by computer. Yeah, 6 months by computer. Not manual. Manual it will take forever. Yeah, manual it will be forever. By computer it can take 6 months. Just to fix the plane. Because you need, you have this 7 dimension, okay? And you need to draw a plane that represent your system. And sometimes when you are draw the plane like this, it's not correct because it's not really represent the other component. So you need to flip this like this, or flip it like this, or like that, until it come to the position that really represent all the components. And this plane is the figure when you plot it in 2D. Good. So should we start again? Okay. So we can read this again. This is a theoretical background. Principal component is a variable reduction process. It's useful when you have obtained data on number of variable, possibly large data, not our example 3 data. It's not large component, and believe that there is some redundancy in those variables. So this means that you have 100 variable, and you can see I understand that y depend on x, z depend on y. This means z depend on x. So there is correlation between the data. This is the meaning of redundancy. There is correlation between them. There is relation between the data. Here you can use the principal component. Because we assume principal component in order to be used, we have two assumptions that the data is dependent on each other and it has linear correlation. Okay? So if the data there is no relation between each other, there is no point to calculate the principal component because it will not give you any results. So redundant means that some of the variables are correlated to each other. Because of this redundancy, you believe that it should be possible to reduce the observed variable into smaller number of principles. Because you understand x is dependent on y. So if I found the relation, the equation that makes sense or makes this relation between x and y, done. I got a new component, right? A principal component can be defined as a linear combination of optimally weighted observed variables. It's linear combination. It's linear combination between x and y. If you have two, x and y and z, and so on. Okay, so it's line. And now we try to define the line. Now you understand what's the meaning of principal component visually, like in graphics. We go now to the mathematical background behind it. We will not go in deep, but just to see the equation. If we say that there is a question and we need to trade these 7 questions from 1 to 7, like my supervisor treat me with consideration, my supervisor consult me concerning important decision in my work, and so on. And I asked you to give a scale from 1 to 7, okay, to answer this question. And then try to correlate this question with each other. You will end with such correlation coefficient. It's a matrix that has the answer. Question 1 with question 1 is 1, 2 with 2 is 1, 3 with 3 is 1, 4 with 4 is 1, because the correlation between question 1 and the question 1 should be 1. It's the same question. The correlation between question 1 and the question 2 can be 0.5. 0.1 and 3 can be 0.3. So there is some correlation, and this correlation, the correlation coefficient is 0.5, 0.3, 0.2, so depend on this question. Okay, and it's very easy to get this correlation coefficient. It can be by Excel. Like, if you have to do the X and Y, and you ask Excel to draw X and Y by bilateral variant, and you say, I would like to see the correlation, it will give you the line and would give you the correlation coefficient, which is the slope of the line. So actually there is mathematics behind it. So actually when you calculate this line, which is the principal component 1, okay, so the line is equal to the point multiplied by the sign of this angle. Okay, so this is the correlation coefficient in between B1, between question 1 and question 2, or question 2 and question 3, and so on. Okay, then we can convert this correlation coefficient into equation. This equation is like this. It's very simple. We have B1, I don't know, B12, okay, B1, B2, Bx, okay. X1 is a value X, X2 is Y, X3 is, so this is actually the variables. It's written here X1, X2, X3, but you can mention it X, Y, Z, the 100 variables that you have. And this one is the correlation coefficient between this and this line. And this is the principal component. It's an easy equation you can extract from your data. And the sum of this equation will give you the weight of this principal component. So actually, this coefficient can tell you how much this component, this principal component, reflect variable 1. So if this equation, for example, you say this P1 equal to 80% or 8.8, it's normally 0.8 or 0.2 or point something. If it's equal to 0.8, this means that this principal component very highly correlated to this X1, and the correlation is 0.8 or 0.9. It's less correlated to this because the correlation here say 0.5, and less here because the correlation is 0.2. In the case of Victoria, when she start to collect her principal component, all the principal component, the sum of this equation equal to 0.5, right? Which is around 50%. Okay, but something like this. So when you are collecting all of this number for all the principal component, will give you the number that how much your principal component represent from the system. In this case is around 50%. In another case, if you are working in the lab, should be almost 100 or near the 100. It can be 20%. It can be 90%. It's depends on you. Okay. Good. Any question? Question online? Kata? Victor? Soraya? No question. Okay, good. No news, good news. So this is just an example from the previous one. We have this variable. So X1, X2, X3, actually in our example is X, Y, Z, A, B, and so on. This is the partition coefficient or the correlation coefficient, and this equation will give you component. How we can do that, just to visualize it in a better way. Say you get this equation. So you develop your model. Okay. And then you said, I have 3 components. C1, this is the equation of C1. But it's just equation, it's not value. How we can get the value? Go to your data and get one row. In this row, you have X, Y, Z, and the different variables. Get the number from this variable and put it here. It will give you the amount, the value of C1. The position, the location of C1, the line on the 2D space. Okay? And by the same way, you can develop a similar equation to component 2. Okay? I would like you to look at component 2, just the equation. Take a close look at the coefficient in front of x, x2, x3, and x7, and so on. And look at the principal component 1 and look at the same coefficient for x1, x2, x3, and so on. If there is different, and what's the difference? Okay, we'll get this and then Victoria. Yeah, please.
The lowest numbers like x1, x2 had the on the C2 it had the lower values. C1 has higher values and turned around when we go further down.
Okay, this is good observation. Vicky? Okay, sorry. She raised the hand before you. Any other comments or any other observation? Yeah, this is exactly the most important observation here. In component 1, if we look at the factor of x1 is 0.44. If we go to component 2, it's 0.1. If we go to the factor in front of x7, for example, is 0.3 in component 1. If we go to the factor in component 2, is 0.39, so it's larger. What's the point here? The point is simple. The point is very simple that each component fetch information from the variables. So actually, when you are saying that component 1, it can include information from here, according to this equation. It's include information from x, x2, x3, x4. x5 is not really because it's 0.02. Right? So actually, these 4 components or these 4 variable is well defined in component 1. If we go to component 2, this variable is very low, but look at x5, it's high. So actually, component 2 represent much better x5, x6, and x7. Good? Okay. This is number of component of extracted. You can read this at home, no problem. But again, you can extract up to the same amount of variable. If you have data that include 100 variable, you can have 100 principal component. But how much we use, this depends on your study. Normally, the first 4 is enough. But you need to collect the total number and you say, okay, this 3 component represent 90% of the system, and I am happy. 90% is fine by me. Okay, 3, okay, fine. I will go for 4, for example, or I will go for only 2. So it's depend on you as a researcher to decide on how many components you would like to use in your system. How much deep you need to go to your system. Yeah, good. Okay, again, this is some characterization of the principal component. The first component characterized in the principal component account for the maximum amount of value. So we got this, like the principal component is the maximum amount of value, maximum amount of information. Second one will be less, third one will be less, fourth one will be much more less. Under typical conditions, this means that the first component will be correlated with at least some of the observed variable. Okay, and we saw the correlation coefficient. So the mathematical example that we got, we see that the first component is correlated with the first 4 variable with certain coefficient. The second component extracted will have 2 important characteristics. First one will account for the maximum amount of variable in the data set that was not accounted in the first one. And we saw it in the equation that the second component analysis actually reflect from x5 to x7 because it was not reflected in the C1. And of course, the most important thing that the second component will correlate with some of the observed variable. It's not important here. This one is important. The second component will not be correlate with the first component. There is no correlation between the first component and the second component. Okay. And so on. So the remaining component will be the same. Like, it will be like contain less information, and less information, and so on. This is just generalization of principal component as proceed in this fashion. Like small amount of variable, and then when you are go to the second one, it will be smaller, smaller, smaller. When the analysis is complete, the result component will display varying degree of correlation between each other, but it should be completely uncorrelated to each other. And this is the point, because you try to extract the data without correlation between them. This is how we calculate it. This is the first principal component. This is the example that I gave to you, like the 3D example. And our data, you see, our data is just distributed in the space, and the first component is just the line between this data. And the second component is the perpendicular line. Well, yep.
Can you go on?
Back here.
Yes.
Yes.
Thank you. I was just the perpendicular line. So that is the whole line is PC2, right?
Yes.
But the PC3, could you just take the cursor and kind of show where the PC3 is?
Well, not easy to visualize it here, but the PC3 is like the perpendicular on this plane. Yeah, makes sense? But now we'll go to the last part of the lecture, the Python part. So now you can see the value of the principal component, right? It's important. It's difficult, right? If you would like to make it for a database that include 100 analyses, you need to do all of these things together and try to plot it in 3D and understand it and so on. But by the machine learning, we make it with only one line. Just one line is enough to get it. Not one line. Clustering with one line. Here, maybe 2 lines. Okay. So actually, there is an example. I promise you that the lecture will be uploaded today. So you can access the lecture with the examples. So we have something called Aries database or dataset. And in this example, we try to like get the principal component analysis from this Aries dataset. Okay. I will go through the code, try to understand it together. and then you will run it at home. Promise? Yeah, but you promised a lot and you didn't make it yet. You didn't, so far, you didn't proceed with the plotting of the figures. Okay, and don't remember that the next report, which will be submitted late of November, it should include some figures. Okay, not for you, for them. Okay, so it's very easy. What we will, okay, Kata, no problem. It's very easy. Import Panda, we need Panda because it's data. Import numerical Python or number Python. Import matplot because we need to visualize the data. And then our famous database or data set, sklearn package. And this is a package that includes this AI and machine learning tools. From the sklearn, we need to get the PCA, the principal component analysis. If you remember, in the previous lecture, we imported the sklearn and we used the k-mean, which is a cluster, the k-mean cluster process in the sklearn. Here we are using different sub-package, the PCA. And we need from sklearn as well to import standard scalar. And this is the discussion between me and Dr. Hunem just during the break. If we would like to use, like to understand the data with a better way. So let me ask you this question just to understand if you got it or not. If we assume that we have data, 3 columns as your data, okay? And we say that in column 1, we have the length, the distance between the cities in Norway. And you say the distance from Tromsø to Oslo, 1,500 kilometers. The distance between Trondheim to Oslo is 600 kilometers, and so on. In the column, the second column is how much the car will produce CO2. Okay, and from Tromsø to Oslo, it produces 0.5. From Trondheim to Oslo, it produces 0.2. And you start to make this principal component analysis using this number as it is. Okay, in order to see the relation between the different parameters. What's the problem here? Okay, it's depend on each other, and this makes sense because longer distance will produce more CO2. There is equation, and the point now we would like to get the principal component analysis between these 3, 4, 5 variables. But there is a problem in our case. Same car, yeah.
Or maybe the terrain was different, more hills or something to use more. I don't know.
Yeah, we can have one column more about the slope of the train. Like, for example, from Tromsø to Norway, the total slope is like 0.1 or so. From Trondheim to Oslo, say 0.2, something like this. So we have a column for train, yes. Still, there is one problem.
The problem is to minimize the carbon throughout the traveling from different places. I think this is a problem.
Yeah, or maybe we can say it's from another way, that the distance that we are using is very large. So if we use, for example, actually we can like read it from both way. We can look, okay, the carbon dioxide that produced is very small compared to the distance as a number, because the number from here to Norway to Oslo is 1,600. It's too much. Okay, it's a very large number. Or we can look at it from the side of the distance, and we can say the distance number or the distance column has very large numbers compared to the other. And this will affect our results. Because in this case, the first principal component will capture the distance as a main factor. And it will come to say the distance is the main factor here. But maybe the distance is not the main factor. Can be the type of car, can be the slope, can be other things. But since this column has large number, it will give an error. And this is why we need to introduce this standard scalar. This is a method in order to scale down the number or scale it up, just to make all the number in our database homogeneous. Okay, so for our online colleague, for example, we can give another example. If we say, for example, we have geochemical data that include measure and trace, and our measure element is measured from 1 to 100 because it's weight percent, and we say that the silica is 70%. Okay. In the other hand, when we are measure the trace element, we measure it with part per million or part per billion. And in some element, it can be 1,000 part per million or 2,000. Like Mushtaq, you from me. BBM or BBB. Okay, so actually when you put this in one database, it will cause confuse because I can see one element which is range maximum 80 from 60 around 80, and I can see another element that is range from up to 2,000, 3,000. So when I start to make this calculation as an AI model, I will use this 3,000 as a large number, and this will be the main component. So I will say all of my analysis will be affected by this element. But actually, this element is just minority. It's how we are measuring it. So we need to standardize the numbers. And this is the standard scalar is used. Good, good. Then we will start to create our database. So we import this data. So import Panda as a BT URL, and then if you just go to this URL, you will get your database, the arrays database. And then we start to load our database in a data frame. So create data frame, DF. And this data frame actually here, it's read from this file. It's read from this data that we just bring from the online. And it read the columns that include the length, the width, the length, and the target. So it will include this five variable. So we'll get 1, 2, 3, 4, 5 variables. Okay, and then we make this DF hit. Who can tell me what the DF hit will give us? Why we add this DF hit?
It will print first 4-5 lines from the data set.
Right. Victor? Who
No,
answers this?
Yeah,
Okay.
it will print.
Yes.
Yeah, it will print
Yes.
first 5 lines from the data file.
Five lines from the data, and it give you
Overview.
this first 5 lines.
Yeah.
The exam is very soon. Okay, we got this in the 3rd lecture or 4th lecture, something like this. Okay, so this is the output of the code. So once you run this code, write it in Python, run it, it will give you this this first 5 lines. another question just to make you a bit woke up. Why we start with why we end with 4? Because we start with 0. That's correct. And why we start with 0? Because it's Python. Yeah, because Python starts normally with 0. Sorry? Start from 0. Okay. So it's like Python. Good. So why we need to standard? This is just some text to tell you why we use this standard scale. Because the principal component is affected by the scale of the data. Okay, and we need to scale down or scale up our data. So actually, we need to measure our data from 0 to 1. We need to reduce the data in order to make it like, no data is weighted much higher than the other. And this is why we added this standard scale. So just this sentence to show you why we use this standard scale. Again, this is just some more text about why we use this standard scale. Again, because the principal component is try to, as you saw here, it's fit with the long length of the variable. So if our variable start from 0 up to 3000, it automatic will understand, okay, this is my main variable, and it will bring it as a main variable. But maybe it's not. Okay. So here, this is a code in order to standard or to scale down, scale up the variable. Get sklearn, and from it import the standard scale feature, and we need to scale down these 4 or 5 features. Okay. And then here they extract x and y. X is actually the variable that we would like to work with. So actually they extracted the features, and y is the target. The target is just ID. And if you remember when we explained the cluster analysis last week, we say that we will not include the ID in our work because ID is not data. It's just a number to define the column, to define the row. So you can say the first row is 1, 2, 3, 4, 5, 6. Makes sense. Python understand it 0, 1, 2, 3, 4, 5. You can call it by names. You can call it whatever. It doesn't matter because it's not data, it's just ID. So here they just remove the target, which is the ID, into one column or one variable called y. And then they apply this equation x, so they create a new x, a new variable, where they standard scale all of our variable, these 4 variable, and transform them to new numbers. And then created a new data frame where they put all the amount, or all the new x. Easy peasy, right? So far easy. Right, top. And if we start to plot the new data, it will be like this. So the old data is, you see the numbers, start from 1, 4, 4, 5, and so on. Here they scale down and they create a new number because they standardized this. So the previous code is just to standardize the data and make it like within the range that is acceptable to start the principal component. So far we didn't start the principal component. Then it's very easy. This is our things. How many data, how many variable we have? It's 4 variable. Length, width, and width again, 4 variable. So we can get how many principal components? 4. Good. So we can say BCA is a variable name equal to BCA, which is a function. We now get the BCA function, and here we need to get only 2 components. We need only BC1, BC2. We don't need to go for the 3 component or 4, only 2. If you would like to go for 4, just write 4. No problem. And then principal component, BCA fit transform. So now they try to fit the data that they got. This is X. So they apply the BCA to the X, and this is our X. This is that produced from here. X equal to standard scale fit transform. This is our variable X. So actually to visualize this variable is this table. So actually here they just get the principal component and they transform or try to apply it on X. Okay. And here they just create a new data frame called principal DF, and they add the principal component. It includes 2 columns. Column 1, principal component 1, column 2, principal component 2. And then here is just to, again, show up the data. So this is our data. This is principal component 1, this is principal component 2. It's already calculated. And then we can plot it. If you like to visualize it, you can plot. You plot principal component 1 against principal component 2 to see it. Okay. And here actually the code is doing something. I try to just explain to you the code, and with the hope that you will do it at home, and with the hope that you will do it sometime next week or week after at the seminar. Because I assume this seminar will be with you, Fiki, right? Next week. Why we don't have this week seminar? This is very strange because actually I didn't see any things today, and we need to discuss this later. Good. And then you can see here something very important. Final data frame. You see it? Final data frame is equal to concat principal data frame with our target and make it with along X. What we are doing here? Can I explain this line? Any answer from here? Any answer from our colleague online? What we are doing here, final DF is equal to principal DF target X. 1. Anyone can contribute here? Well, it's easy peasy. If you remember, when we start our analysis, we extract 2 things. We extract X, which is our data, and we extract Y, which is our target, the ID. And here, we just create a new Excel table, a new data frame that includes the principal component and our ID. Because you don't need to lose your ID, because if you lost your ID, there is no point to analyze. You have numbers, but you don't know which number is related to which sample. So you need to add the sample after that. And then we have the visualization. I think it's easy peasy for you. You can go through this visualization things. I assume that it's easy for you, right? Like create figure, plot the figure, You can see here 8 plus 8. So actually, this is a figure size. You can see here the subplot. So actually here we plot one column. Actually, it's one. So actually, it's one column, one row, and only one figure. So it's one figure. It's only one figure. Okay. And then here, just try to set up the X labels, the Y labels, the title of the figure, the color of the figure. So they just try to play with the figure. And then this is our figure. Okay. So you have the code. You have the database. You have the link to the database. You have the code. And you have the result of the code from each step. Again, try to review it again with you. The first step is to load the data and get the data out and put it in this DF, this data frame. The second part is to standardize the data, try to scale it down, scale it up. Okay, and save the new data in a new data frame called X, which is this one. Then make the principal component analysis. So actually, all of the today lecture is just one line. This one, you see, principal component equal to BC fit transform X. This is our lecture today. This line, easy. Okay. Then make the plot. Then see the plot.
The question, but I thought you said earlier that there is no correlation between two, where they just explain less and less information.
Yes.
While this figure shows PC1 and PC2.
It's not correlation. It's just visual representation. Yeah. Yes. Nothing to do. It's just, yeah, it's just visual representation. And the good thing now, you can see 3 cluster. So actually, now you start to think, okay, what I should do? Should I do cluster first and then principal component, and or principal component and then cluster? Because the last lecture was clustering, was cluster the data. And then today we make principal component. And the principal component, it's aimed to do clustering. As you see here, just we plot it and we see 3 clusters. Okay. What we should follow, clustering, principal component, or principal component, then clustering. I don't know if Soraya was us or not, but maybe this also question can go for you. Cluster first component or first component and then cluster. Sorry?
I'm here. I'm listening.
Yeah, do you think you can answer this question?
Can you ask again?
How we can, if we would have a data, like your data, for example, and we need to run the principal component, which is better to run the clustering to see how many cluster we have in the data, and then run the principal component, or run the principal component and then make the clustering.
I think run the principal component first.
Okay, so run principal component first and then clustering here.
Yes.
So this is one answer. Any other answer? No, you just already did your answer. So we need just to see another answer, just to.
Okay.
Okay, so you answer semi-correctly, Lynn.
But I think, yeah, I think I agree with that.
He said two things.
Yeah.
You are insecure to answer. You go for both, yeah, okay. Who would like to go for both? Okay, so Vicky is like Mushtaq, they would like to go for clustering first, right? But doesn't matter, maybe both, okay? Yeah, depend on the data. So we have two different answer. Soraya in Egypt said principal component first and then clustering. Master student, Lisa said it's not secure. She
Just don't see how it
can affect different. Yeah. Anything from here? You don't know. Anyone from other colleagues online? Because actually this is the last slide. Yeah, this is the last slide. And actually this will send us back, the answer of this question will send us back to the third lecture, cleaning up the data. So actually this is like a repeated process. You can start with clustering, then principal component, and then recluster again. Or principal component, cluster, and then another principal component. It's not one step ahead. Like, you can make it, and then you discover, I feel that this variable, after you make this clustering and you spend a week just to write your code to make this principal component, and then you came and say, but I see this component one is really affected by this variable, which I don't think it's a correct one. So I need to remove this one, or I need to scale it down, or I need to change it, or there is a problem with this variable. So actually all of this process, just you need to come, return, make it again, and return, and so on. It's not one straight ahead. Good. So I assume that's all. I would like to thank our colleague online, and thank you. And then I would like to ask you one question for the people who are here. Thanks, Mayada. About why we don't have a lecture this week or a seminar this week.
It says here that we have data sorting and storing on the Thursday, the 31st.
I know why. Because I have it here. Okay. Data sorting and storing. When I give you the date for next week. No. I mean when? Is it? Yeah. Is it Monday, Tuesday? Thursday. Okay, so I know why I did that. Okay, so actually we will have a seminar this week for the master students, and this will be Thursday. So I don't know, Kata is not here, but we have to inform her that we have this seminar Thursday at 10. So the question is, and this is good question, do you, Vicky, and you, Mushtaq, have time on Thursday from 10 to 12? Thursday, this Thursday, after tomorrow. For a lecture? Yeah. Yeah, but if you have time, we can have this Thursday as a lecture, and then Monday we'll have another lecture, and then in this case we will need to find only a slot for a seminar. Yeah. Agree, Mushtaq? You don't need to agree because you are here anyway. Okay, good. So we will make this change just in order to help ourselves. Thanks to the ruling. So this Thursday we will have a lecture, and this will help us not to like go through the doodle. But please try to fill the doodle because most probably we'll need one lecture. And then the next Monday we will have the seminar or our lecture online. 10, yeah. 10. This Thursday is good. So thanks, people. So you can leave now, the online people. No, this Saturday.
Yes, Thursday. Sorry.
Don't give wrong information.
Oh, yeah, so true.